Question E1. This question is about the properties of a star. Describe what is meant by a constellation. Well, a constellation is a group of stars, a collection of stars that form some sort of pattern or group as viewed from the Earth. So they look like they are near to each other when viewed from the Earth. Obviously, I'm just writing in a few major words there. These may well be far apart from each other. But a stellar cluster, these are stars that are actually bound together. They're bound together gravitationally. They're relatively close together, relatively close in comparison with the universe and galaxies and so forth. In the next question here we have some data for the variable star Betelgeuse are given below. So the average absolute magnitude is minus 5.1. We've got the apparent magnitude is 0.6. We've got the apparent brightness, and we've got the radius is 790 solar radii. So the luminosity of the sun is 3.8 times 10 to the 26. And the surface temperature is 5,700 Kelvin. Show that the distance from the Earth to Betelgeuse is about 4 times 10 to the 18 meters. Now, when looking at the information that we've got to choose the formula that we're going to use. And because I'm given the absolute and the apparent magnitudes, that immediately directs me to this formula over here, where I can work out d, which is the distance. But remember, this distance is in parsecs. So I can put this in here. So I'm going to use my m minus my capital M is equal to 5 log of d over 10. This is the log to the base 10, and I put in here my values. So that is 0.6 minus 5.1 is equal to 5 log d to the 10. That's going to be plus, because a minus is positive, so it's going to be 5.7. And I'm going to divide through by this 5 is equal to the log d over 10. When I do the calculation there, I get that 5.7 divided by 5 is equal to 1.14 is equal to the log d over 10. Now I've got to change this from my log form into my exponential form, so it's the base 10. So when you have this over here, it becomes 10 to the 1.14 is equal to d over 10, and I'll multiply both sides through by 10, cancel that, and I'll get my d. So I get, when I put that in, I get 138, and that's parsecs. But we don't want it in parsecs, we want it in meters. So I have to convert from parsecs into meters. And to do that, we go to the front of the data booklet, and you'll see your conversions there. And to get our distance in meters is going to be 138 parsecs. And each parsec is 3.26 light years. And each light year, we are told, is 9.46 times 10 to the 15 meters. So we have that, and we multiply that out, we get about 4.3 times 10 to the 18 meters. Okay. Now I've left it as 4.3 because we seem to be given quite a lot of information in two significant numbers. So determine, in terms of the luminosity of the sun, the luminosity of Betelgeuse. Now, in looking for the luminosity, I've got two formulas that give me luminosity. I've got this over here, and I've got this over here. Now, I don't have anything about the temperature of Betelgeuse, but I do have this information. I've got that, I've got my apparent brightness, and I've just worked out the distance. So I'll definitely use this formula over here. And so we want the luminosity, that's going to be B times 4 pi d squared. So I put that in. I've got my apparent brightness there. That's going to be 1.6 times 10 to the negative 7 times 4 pi times 4.3 times 10 to the 18. And you see that squared there. Don't forget the squared. It's going to be squared. Now, it actually says in terms of the luminosity of the sun. So this is going to give me the total luminosity in watts. So what I'm going to do is I'm going to divide this by, I'm told here that the luminosity of the sun is equal to 3.8 times 10 to the 26. I'm going to divide this by 3.8 times 10 to the 26. And that will give me my luminosity in terms of the luminosity of the sun. Because this would be, each time I divide this, if it goes into it once, then it will be the same as the sun. If it goes in twice, it will be twice the luminosity of the sun, and so forth. And when you do this, when you do this whole division, make sure that you just put this into your calculator correct. You get 9.8 times 10 to the 4, the luminosity of the sun. And this is the luminosity of Betelgeuse. Then calculate the surface temperature of Betelgeuse. Now, we've got the luminosity in terms of the luminosity of the sun. We've got our area in terms of, we can put our area in terms of the surface area of the Earth, because we are told that the radius is 790 solar radii. So I can use those facts. Obviously here, the formula I'm going to need to use is this one over here. We don't know anything about the wavelength. That's when you've got Wien's law. That's when you've got the maximum wavelength where most of the energy is coming, and use that. But so we're going to use this formula over here. But it's going to be as a ratio. So let me just start over here. So we got the luminosity of Betelgeuse is equal to sigma. The area, remember the area for a sphere is 4 pi r squared. So I'm going to get 4 pi r squared. Now it's 790 times the radius of the sun. And we're going to need to square that. And then times temperature of Betelgeuse times to the power of 4. Now, I can put that over the luminosity of the sun, and that's also sigma 4 pi, that's rs squared, and the temperature of the sun to the power of 4. Now obviously these cancel, these cancel, these cancel. The luminosity of Betelgeuse is, as we've already worked out, is 9.8 times 10 to the 4 the luminosity of the sun. So when I divide that, that cancels with that. So I can have that. And this T of the sun to the 4, that's going to be, we know that that's 5,700. So I'm going to get TB, the temperature of Betelgeuse, is going to equal 9.8, sorry, that was to the 10 to the 4, 9.8 times 10 to the 4, and we're going to multiply it by T to the TS is 4, so that's 5,700, and that's to the power of 4. Notice here when I square this, these two will also cancel, because that will also be squared and squared. So I'm just going to be dividing this by 790 squared. Then I'm going to take the fourth root of this. When I take the fourth root of this, obviously that just cancels, so I've just got that. So I just take the fourth root of that, and that will equal the temperature of that. And when I do that, you get a value of about 3,600 Kelvin. Actually, they accepted from 3,000 to all 3,500 Kelvin when you do that to calculate the surface temperature of Betelgeuse. Okay. So it says on the diagram, on this diagram, on the Hertzsprung-Russell diagram above, label the position of Betelgeuse with the letter B. So we know that it's the luminosity, the relative luminosity. So this is the sun. In terms of the sun, remember, it was about 9.8 times 10 to the 4. So you're looking at a very close to 10 to the 5. So here's 10 to the 4, 10 to the 5, 10 to the 6. You're sort of in the middle between there. And your temperature was 3,600, 3,500. So you're sort of roughly halfway in between. So it should be somewhere over there. So this is one of these. This would obviously be a super red giant or red giant, super red giant. Red in color but highly luminous. So it's got a very large surface area, as we saw, 790 times the radius of the sun. And sketch a likely evolutionary path. So what's going to happen to this, it probably came from, this would be your main sequence, something like that. So it probably came from up here, because it's quite big, probably came up here, and it will go around like that. That would be the likely path that it will take. Then it says some stars, such as Betelgeuse, are in combination with a companion star forming a spectropic binary system. Describe and explain the characteristics of a spectropic binary system. So what actually happens here is that in a binary system, you've got two stars. If we look at sort of like from a top view, you may have Betelgeuse over there, and you may have another star X over there, and they would be revolving around each other, something like that. So if the Earth is over here, if it's going, when it's coming this way, what's going to happen is that the light coming in this way, it's coming towards us, will be blue shifted. And the light from X will be red shifted. So at this stage over here, you're going to get a difference in your spectral lines. Your spectral lines there will be a gap in them. Now when X is over here and B is over here, and they're going like this and like that, then the light coming this way and this way will not be Doppler shifted. And so the spectral lines will come together. And when Betelgeuse is over there and your X is over here, then you're going to get the light shifted in the other way. You're going to get a shifting of the spectral lines in the opposite direction. So because of the Doppler effect, you get this changing of the spectral lines as they rotate